In this second lecture about stochastic models, we're going to focus on stochastic epidemic models proper. So the previous lecture, I sort of showed you the underlying stochasticity to deterministic models. This time, I want to look at proper stochastic models. Okay. One thing that I will point out, there's practicum number 3, in which I will go into the analysis of this type of model. So here I'm not going to spend so much time on the analysis, actually almost no time on the analysis at all. I will do so in the practicum. I am going to illustrate some things and show you pieces of code, but nothing more than that. So the first point will be to, like sometimes I'm circling around, why is it that stochasticity matters? And I'm going to show you explicit examples where using a stochastic model as compared to a deterministic one changes the outcome quite radically. And then I'm going to detail the 2 types of stochastic models that I'm going to be dealing with in this course, which is discrete time Markov chains and continuous time Markov chains. So let me move to a smaller me. First of all, as I said, this particular course is user-oriented. I'm not going to look at the algorithm, the math, or whatever. I'm going to really focus on how you use those algorithms. The code is available in the GitHub repo. You will see there's a bunch of programs there that deal with simulating continuous time and discrete time Markov chains. And I'll point out that some of the slides that I have here and in the practicum are inspired by slides that were given to me by Linda Allen. So if you're looking for resources about stochastic epidemic models, I really recommend some of her work, which is quite insightful on the topic. And I'll point out, for instance, this book, The Introduction to Stochastic Processes with Applications to Biology. There's also a primer that she wrote in the Infectious Disease Modeling Journal about stochastic epidemic models. And I refer you to these works that are much more comprehensive than whatever I would be able to say here today. So to begin with, why is it that stochasticity can be important to take into account at times? And again, I will come back to the what permeates this course. It's like you don't need stochasticity if you don't need it. But there are contexts in which you will need stochasticity. And it's a good thing to ask yourself the question, do I need this type of model? What will this bring to me in my analysis or my comprehension of the problem? And this is true for stochastic models, but it's true for ODEs, adding more compartments and so on. So this sort of permeates this whole topic. So I'm going to take the SIS model without demography in this lecture. I'm going to assume that there's a constant population P star. And typically, if we are looking at a model with mass action incidence, in that case, R0 would be something like this. Actually, it would be times S of 0, not P star, but typically we assume that at the beginning of the period of interest, S of 0 and P star are very close. There's just a few infectious in the population, and essentially S of 0 equals P star. Now, let me make let me show you something quite striking. So if you think about what we have seen so far in the course about the deterministic world, what we have seen essentially is that R0 encapsulates a lot of the information we need. It is the bifurcation parameter that tells us whether, so for instance, if we're looking at an endemic SIS model, whether the disease dies out or it goes to an endemic equilibrium. So let me consider an endemic SIS model. And so if R0 is less than 1, then the disease dies out. And if R0 is larger than 1, then the disease goes to an endemic equilibrium, which is 1 minus 1 over R0 times the total population. So in the slides that I'm going to show you, I'm going to use a total population of 100K, 100,000 people. I'm going to take a recovery rate of 1/5. That means an average duration of the infectious period of 5 days. I'm going to assume that I'm working in days. And I'm going to show you several values of R0. 0.8, so something where things go extinct, 1.5, and 2.5. And beta, I'm not going to specify, only insofar that it's given by the knowledge of the other parameters. Okay, so I don't really care about beta. I just set it by assuming that it's such that R0 equals to those values that I'm prescribing. If I simulate the system, let me get myself out of the way. If I simulate the system, what I see is the following situation. When R0 is less than 1, I remain very small. If I start with 1 infectious, I will eventually go to 0. So the limit, I never reach 0 explicitly, but my limit is 0. The number of infectious, okay. If R0 is 1.5, the disease picks up, and after a while we get about 35% of the population that's infected concurrently, okay, because there are people recovering, but it's an SIS model, so the people that recover become susceptible again right away, and then they become infected potentially right away. So there's a flow from and to the S and I compartments, but that stabilizes around 35% of the population. And if R0 is 2.5, then likewise, I go to an endemic equilibrium, but this one has about 60% of the population infected at a given instant in time. Now, what's going to happen when I look at a stochastic model of the same process? So let me maybe put myself here. So I said well, maybe here. In a deterministic world, R0 rules the world, okay? It determines what happens to your system. In a stochastic context, rules each is more appropriate. So what I'm showing you here is a certain number of simulations, which in stochastic processes we typically call realizations. So this is a certain number of realizations of a continuous time Markov chain that's analogous to the SIS deterministic model we were just looking at. That starts with, I believe I started with 2 infectious individuals here. And so each one of those black curves and blue curves corresponds to a trajectory. So the big difference with deterministic and stochastic systems is that in a stochastic system, I can never have 2 times the same trajectory. Each trajectory will be unique. But you see a global tendency here. I've taken R0 equals to 1.5. If you recall, when we had R0 equals to 1.5, we were going to about 30K out of 100K that were infectious. Here, well, it looks like where the bulk of the solutions are is around 30 to 40K. So it matches quite nicely what we have, with, of course, variation through time. But there's also all these blue curves that I've sort of highlighted, and those correspond to solutions, realizations, where the disease went extinct over that 100 days time period, okay? So regardless of the fact that R0 is greater than 1, I have a certain fraction of the realizations, a certain fraction of the simulations, if you want, that have gone to 0 over that time period. Okay, and that's very different from the deterministic case, because in the deterministic case, we saw that all solutions, when we started with 2 infectious and an R0 equals to 1.5, well, we went to that endemic equilibrium. Here, there's a certain fraction of solutions where the disease goes extinct. And actually, let's look at what happens in practice. So let me take the same problem as I was taking before, but instead of taking a fixed R0 on the x-axis here, I am increasing the value of R0. And on the y-axis, I'm counting the number of simulations which have extinction over that 100 days time period that I'm considering. So 100 days is not a lot, okay? I should point out, if we wanted, maybe we could do more, but this is just for illustration. So when R0 is less than 1, we're starting with an I of 0 that is quite small. And what we see is that essentially, I don't remember how many simulations I ran for this, probably 1,000 or 10,000. So each one of those points is the average, well, it's the proportion of 10,000 simulations, whatever number I took, that go extinct, so that correspond to one of those blue curves that we had in this figure. So it's a simulation that ends up hitting the I equals 0 axis at some point in that time window. So when R0 is less than 1, you can see that essentially everything goes to 0. Okay, there might be, this is starting to drop off a little bit, but that's it. So this is very much like the deterministic case. We go extinct, or if a disease goes extinct quite quickly. But then you can see what happens when you start to take values of R0 larger than 1. So in the deterministic case, those cases with I0 equals to 2, so with a positive initial condition in the number of infectious, would automatically go to the endemic. And you can see that, for instance, for low values of R0, well, for values of R0 close to 1, well, you still have, for instance, this is probably 1.1 or something like this, or 1.05, I don't know how many, I think it's 1.05 probably. You can see that there's still a huge fraction of the simulations that are going to 0 over that time window, which is not something we'll observe in the deterministic case. Okay, they'll all go to the endemic, whereas here we're seeing some simulations go to 0. And even with a large R0, so a disease that's quite apt to propagate, okay, on average, each infectious individual, when I'm here at 3 or 3.5, each infectious individual infects on average 3 new people. But despite this high infectiousness, what I see is that I still have a positive number of cases, simulations, where the disease goes extinct. Okay? And that's quite different. And that's, for instance, some of my work around COVID has concerned importation of cases. When you're thinking about how a case comes to a new location, well, one thing that you have to realize is that there's probably way more cases arriving in places that don't have cases, for instance, than we're aware of. But a lot of them go extinct quickly, okay? And this is important. So it means that even if you have a disease that has an R0 of 1.5, say, there's still a certain fraction of cases where the disease doesn't manage to kick off. And if that's what you're interested in, then it is important to take that fact into account. Okay, and that's one case, not the only one by far, but that's one case where considering a stochastic model compared to a deterministic model makes a lot of sense. Now, today I'm going to show you, and I've discussed this already, but I'm going to show you two types of Markov chains, discrete time and continuous time. I'll point out that you could also look at branching processes or stochastic differential equations, like I said in lecture 6. I believe it's lecture 6. Now, discrete time Markov chains. And again, I'm going to sort of articulate my presentation between this lecture and the practicum on stochastic systems. So you learn a little bit about them here, and you learn a little bit more about them in the practicum. This felt like a sort of good way to introduce things rather than go directly into the topic. So what's a discrete time Markov chain? So it's a stochastic process where you have a probability vector that has entries describing the probability that at time t the system is in a given state. So if you remember when I was in the previous lecture, when I was explaining that time until change, we had a system in two states. Here we're allowing n states. This is weird. I don't know why this hash is here, but never mind. So we have a probability vector. So if you have a system that's potentially in n states, then the probability that it is in one of the states is 1. Okay, so that's what this equation here says. It just says, oops, I should, this sum here is telling you that you have to be somewhere. You have to be in one of the states, but because you're considering the probability that the system is in one of the states, you end up summing all those probabilities, and the entire space of potential states has to have size 1. Okay, and what you do is then you say that the evolution of the state, so this is the probability vector, it's the state of the system, and that evolution is governed by this difference equation. So the probability vector at time t plus delta t is a function of, well, I mean, it's a linear function of some matrix A evaluated at delta t times the state at time t. Okay, so delta A of delta t is what we call a stochastic matrix. All its rows equal to 1, and we call it the transition matrix, okay, for the process. And what it does is it encodes the probability that the state is Si at time t plus delta t, given that it was Sj, these should be capital letters, given that it was Sj at time t. Okay. And these x's then are a sequence of random variables that describe the state. Typically, we're going to look at, in this case here, at homogeneous discrete time Markov chain where A is not a function of the time step. And in particular, I mean, it can be a function of a time step, I shouldn't say it this way, but it doesn't depend on time. And typically, we recast the time so that the time step ends up being 1. So we think about generations, for instance, rather than t plus delta t. We think of generation t plus 1 given generation t. Yes, this is an important remark. Let me. This is an important remark. The discrete time Markov chain objects live at the interface between two types of people, probabilists and linear algebraists. Probabilists, oftentimes, if you take probability books, they think of the vector of states as a row vector, okay? And therefore, they write the evolution of the system as P of t plus delta t equals P of t row vector multiplied by matrix. Whereas linear algebraists prefer column vectors, and therefore they often write the systems as P of t plus delta t as a column vector is equal to A times P of t, okay? It will be evident in whatever reference you're using, if they're using one way or the other, but I make that remark because since I use references from the two contexts, it is not impossible that these notes would contain one matrix that should be transposed instead of what it is. Okay, I've tried to fix them, but sometimes they do escape attention. It just is a matter of being consistent, and for instance, when you're writing a paper instead of notes like this, you should check that everything is consistent. And here I'm talking to people that do teaching as well, because in the school there were, in the lecture series, there were people that were not only students but also teachers that came to learn about math epi. I'll say that DTMC, so discrete time Markov chains, as a teacher of modeling, the base theory uses a lot of linear algebra and graph theory. And my experience is that students, like I've designed a variety of modeling courses, like a second or third year modeling courses, and very often discrete time Markov chains is the part of the course which the students prefer. Okay. There's two types of Markov chain. Well, there's many types of Markov chains, but the ones we'll be considering here mostly are regular discrete time Markov chains, and those allow to consider the equilibrium distribution of the probability vector. Whereas there are absorbing discrete time Markov chains, and these correspond to systems where the transition matrix is so-called irreducible, and those allow to consider the time to absorption, the mean first passage time, and so on. So these are very important problems that I'll detail here, but also in the practicum. One last remark for references on discrete time Markov chains, in particular on the matrix aspects. There's a very good book of Kameny and Snell that you might want to look at. Let me take an example because we'll come back to this one. This is a fundamental example, and I think it's really important just to illustrate the type of problems that arise. This is the discrete time Markov chain for an SIS model. And the idea is that the model is formulated as what's called a random walk. So it's slightly bizarre random walk, but so you consider a total population P star, and then you say that, as we've done many times before, the total population is constant, therefore I can forget about S and just use P star minus I. To simulate as a discrete time Markov chain, what I'm going to do, is to consider something that is akin to the gambler's ruin problem. So essentially we have a chain like this where the states are the number of infected and infectious in the population. So that number can go from 0, so there's no infectious and everybody's susceptible, to P star, everybody's infectious and nobody's susceptible. And what happens is that we are going to have 3 possible evolutions. And of course, this is just assuming that every time I'm going to infect a single person, which is quite a simplification, but okay, it's acceptable under some circumstances. So the way we are going to move up in the chain is as a beta Si times delta T. Okay, so beta Si is, well, how many susceptible and infectious there are in the population. I say S, it's P star minus I, of course. The movement left is through recovery, so gamma I times delta T. And finally, there is the possibility that nothing happens, and that's the complement probability to these 2 probabilities, okay? And this happens per interval delta T. So there's always, when you're writing this type of model, you have to bear in mind that yes, sorry, I had to cut for a second. So yes, one point here is that typically what you assume is that delta T is small enough that only 1 infection event or 1 recovery event will take place per time delta T, okay? And this is quite a stretch, and in practice, if you're trying to run a model like this, you will see that it's sometimes a little difficult to set what the time step is. But in effect, this is what we envision. We envision that delta T is small enough that the rate of things changing, well, I mean, that the number of events that are happening does not change too much. And only 1 event is possible. Now, if you want to model this using a discrete time Markov chain, you need a transition matrix. And the transition matrix in this case is very simple. And I should come back to the model in a second just to show you. So for each possible state, except the first one, where I equals 0, and the last one where I equals P, there are 3 possibilities. Mu is the rate at which you recover, okay? So this takes you down 1, so that's why you're beneath the main diagonal. Lambda is the rate at which you move, a new infection is created, and so this is above the main diagonal. And sigma is the rate at which, the probability that nothing is happening, okay? And that is the main diagonal. And the 2 extremes are these. So, and this is an important state. So if I go back to this graph, one thing that you will see is that when I go from I equals 1 to I equals 0, and then I get to I equals 0, if you look at this arrow, when I equals 0, it doesn't exist, okay? This is 0. So that means there's no transition possible out of this state I equals 0. And we say that the state is absorbing. And with probability 1, we end up stuck there. Likewise, this state is a bit different because once you get there, well, you can stay there, of course, but you can recover, but of course you cannot move right. Okay, so that's why this matrix has this very regular structure, except for the first row, where you stay in the same location with probability 1, and the last row, where you can either stay in the same place, or you can move left, but not right. Now, how would we simulate this? So as I said, this lecture is going to be a mix of simulation and explanations, let's say, and we'll move to the more details later. But let's look at this. So I need to make a transition matrix, and for this it's quite simple. I'm going to, for each row, but it's not the first row, I'm going to say that I is the number of a row minus 1, of course, because here I equals 0, so everything is shifted left by 1. And so because I need to go all the way to P star, I need one more entry, of course. So here, what I'm saying is there's a movement left and a movement right. I compute these probabilities and I put them there. I then make my last row. And my first row, anyway, is simple because what I need is every row in this matrix must have sum 1. Okay, so what I do is I don't fill the diagonal entries, and the last thing that I do is subtract the row sums, each row sum, from the diagonal entries. And that automatically puts a 1 at the top left corner and 1 minus the sum of the probabilities in the rest of the diagonal. And that's one thing that you can see. So when you're making this matrix, it is very likely that if you take a delta t that's too big, okay, there's a delta t here. If you take a delta t that's too big, then those off-diagonal terms might have a sum more than 1. And that gives you, so of course this is not possible, I need to sum to 1 and I cannot have negative numbers. So that is one way to control the delta t. You want a delta t that is such that you're always, all row sums must be less than 1. All row sums without the diagonal. So this is the matrix. Let me show you one way that you can simulate it. You can use this DTMC pack, which is a package for looking at discrete time Markov chains. And what I'm saying here is simulate 20 chains where the transition matrix is this. This is my initial condition, and I impose some final time. And what you get is something like this. So here again, I'm still indicating in blue the solutions that go extinct, well, the number of infectious going extinct during the realization. But for the others, of course, I should have used different colors because it's difficult to tell them apart. You can see what's happening, okay? And that's 20 realizations of the same Markov chain. Markov Chain is another package that is actually much more comprehensive, and that is worth taking a look at if you're looking at this type of system. You can invoke it essentially the same way as we did before. I'm giving a name to the states because it's useful to give them a proper name. So I'm just saying that the states are I0 to I whatever pop is. The transition matrix, as before, is T, and I name my chain SIS. One remark, if you end up using this, Markov chain actually overrides this thing that I was complaining a little bit about, where star represents the Adamant product. So when you have a Markov chain, when you load Markov chain, star becomes the regular matrix product. Okay. So let me show you what this looks like. I will go into more detail about this in the analysis part, but it is interesting. So what's the chain that we created? And you can see that the program is able to provide quite a lot of information. It says that the closed classes are I0, recurrent classes are I0, transient classes are all the others. The Markov chain is not irreducible. This means it's an absorbing Markov chain, and the absorbing states are I0. Okay, so the program is, the library is able to provide you with some information about the Markov chain that you're considering. And it's able to do a lot of interesting things, like tell you what the absorbing states are, what the steady states are. It can give you a matrix or vector of mean first passage times, etc. So this is quite this is quite an interesting package in the sense that if you're using discrete time Markov chains, it really allows you to study the problem quite well. And we'll come back to that. Okay, so when we're looking at the practicum, you will see these things again. Now, let's look at continuous time Markov chains. So continuous time Markov chains, as the name implies, are chains in which time is continuous. So remember that the chains we saw before had a transition each delta t. When we have a continuous time Markov chain, we assume that delta t goes to 0. And what happens is that we're now looking at transition times, and what ends up happening is that the transition times follow an exponential distribution. Okay? And that exponential distribution is parameterized by the state of the system. And I will show you many examples to sort of illustrate the fact that those continuous time Markov chains, they're actually very close in behavior, not overall behavior, but they represent ODEs very well. So let me first explain how you would go from an ODE to a continuous time Markov chain. Sorry. This is quite simple. So if you think about it, an ODE focuses on the state variables. So if I'm looking at my SIS model that I've been playing with from the beginning, what happens is that I look at the compartment S and I look at a mass balance equation, and the evolution of the number of S in the compartment depends negatively on outbound flows, so in this case minus beta SI, and positively on inbound flows. Okay, the same way, if I look at I am positively influenced by inbound flows and negatively influenced by outbound flows. Well, if I want to switch gears and think about a continuous time Markov chain equivalent to this problem, what I need to do now is to think in terms of arrows. So in an ODE, I'll be writing a mass balance equation for S and for I. In a continuous time Markov chain, I will be focusing on these arrows. What do they mean? And it's quite simple. Let's forget the left column for now. That arrow here means that there is loss of a susceptible and gain of an infectious. And the other arrow is there is gain of a susceptible, recovery, okay, and loss of an infectious. And what happens is that the weight of these events is given by beta SI and gamma I. Okay, so this is exactly like we had before, except that here, if you think about it, these are weights. So the weight of the event moving from S to I is beta SI, and the weight of the event moving from gamma to I, from I to S, is gamma I. Okay. And so this is the most used way of thinking about these models. It's what's called Gillespie's algorithm. And I'm going to, again, use only the I equation. Okay. So how do we go from the weights to the probabilities? Well, this is the algorithm as it works in general. So I'm going to start with some initial time t0 and some initial value I of t0. okay, I0. And then I'm going to keep increasing the time. And first, I'm going to compute that psi t, which is beta Si plus gamma I. So this is the total weight of the potential events. Okay, so remember when we were looking at this is the weight of this event and this is the weight of this event. So all I'm doing is summing those weights. And then I said there's an exponential waiting time for events to happen. And how do I find that exponentially distributed waiting time? I simply draw a random variable from an exponential distribution with parameter this total weight. Okay. So this gives me tau t is going to give me the time until the next event takes place. And then I have to decide what event takes place. And the events that can take place are the ones that are encoded by these arrows. Okay, so I can either go from S to I, have an individual go from S to I, or have an individual go from I to S. So these are these transitions here. And so what I'm going to do is I'm going to make a vector, and you see that this vector, the weights are divided by psi t. And since psi t is the total weight of the events, the entries in this vector are probabilities, okay? Proportions at least. When I divide psi t, when I divide this by psi t, I get 1. Okay? And then what I'm going to do, so I have a vector that has an entry that's non-zero and an entry, this one is going to be, you can do it several ways. I mean, the way you do this actual step depends on the algorithm, but it essentially always boils down to this. This is the weight of the first event, infection, and this is the weight of the second event. But here I've only got 2 events, so the sum of the 2 weights is 1, so the second event is simply probability 1. And what I need to do then is draw a random number from a uniform distribution in 0, 1 and find which of these 2 events happens. So suppose this has probability 1/2 and this has 1/2. So the content of a vector would be 1/2 and 1. Then if the number that I draw is less than 1/2, it's the first event that happens. And if it's more than 1/2, it's the second event, and so on and so forth. Okay. And indeed, you find the position that puts you in the vector where you want to be. And depending on which entry in the vector took place, you either gain an infectious, and that's a new infection, or you lose an infectious because there's recovery. And then finally, you move the time by this tau t that you determined the time before, while you're still with tau t less than, with t less than tau tf, well, you continue. And so now the new state is going to be used, I should use capital I's here, but never mind. The new weight is going to depend on these new values of I. It's going to give me a new time until the next event, and so on and so forth. But I'll point out that, okay, we'll implement some Gillespie by just for ourselves, but and I recommend doing it. But there's some very nice packages to allow you to do it well, and those packages have the non-negligible advantage that they implement what's called tau leaping. And I'll come back to tau leaping in a second. So let me show you using a library. So this is one of the libraries that you can use, which is called Gillespie SSA2. So I set my initial conditions. So I have defined, I'm not showing it here, I've defined an I0. And so I say that the initial condition is S is P star minus I0, I is P star, is I0. I define my parameters. I define my reactions. So that's the reaction rate. That is what it does to the state. So, and that is the name that we give it. So here this is saying, okay, if beta SI is the propensity, that's one of the other names that is used for that. If beta SI is the weight of the events, then that event consists in reducing S by 1 and increasing I, and I'm going to call that a new infection. And likewise, with weight gamma I, the event consists in gaining an S and losing an I, and that's a recovery. Then I can simply call SSA, which is provided by this library, giving the initial states, the reactions that I've defined, the parameters that I've defined. Here I'm saying use an exact method, not a tau leaping method, and introduce whatever the final time is, and then your solution can just be plotted. And here this is one single realization of this process. Okay, the SIS process. I've taken a very high value, I don't remember what it is, but I took a large value of R0, and I also picked and choose to get a solution where things are increasing. Okay, but that's just one illustration. And in fact, you can run many of those. And let me point out something that's quite interesting. So this is a certain number of realizations. So these are the black curves. And I'm also showing you the mean of the process, the mean conditioned on non-extinction, and what the SIS ODE does. And you can see that the SIS ODE is tracking somewhere in between the mean condition. So this, of course, is a case where R0 is larger than 1. This is tracking between the mean conditional non-extinction and the mean of the process. Okay, that mean is much lower because there's quite a bunch of solutions that go to 0. And of course, if you're taking the average, the mean here, I should make this clear, the mean is at a given instant in time, I'm taking all the different values of the realizations of the Markov chain, and I'm taking the mean of these values. So of course, if I don't condition on non-extinction, I have quite a few of those solutions that are equal to 0 identically here. Okay. And let me point out, while I'm talking about this, you'll see the code is in the code directory, but one thing that I want to point out is that when you want to compute a mean, like I did with that red or that brown curve, you have to interpolate the solutions, because remember what I said, so the time between events is exponentially distributed. It's a random process. So each one of those solutions can change at times that are very different. Okay, if you look at this solution and the solution just beneath it, this solution goes through these transitions here. That solution that's beneath it might go through transitions at times that don't align. So if you want to sort of plot or compute means or things like this, you typically have to interpolate. You take a very fine grid of time, and then you interpolate each of your solutions to this very fine grid. And when you look at the code that I've provided, you'll see that there is an interpolation step that comes in. It's just in order to be able to do this red and the brown curve. Now, let me show you when things go bad. I talked earlier about the fact that we could use what is called tau leaping. So let me explain why this will come in, because there are limitations to this method. So the inter-event time, so remember what happens in the Gillespie algorithm. I evaluate the weight of all the events. I use this weight to determine the time at which the next transition took place. So that inter-event time is exponentially distributed. So when I'm computing the weight of all possible events, this sum of what gives me the xi, and drawing tau t from this exponential distribution with parameter xi t, well, what happens is if xi t becomes very large for some t, remember that xi t is the parameter, so that means that the mean of the inter-event time from which we're drawing is 1 over xi t. So if xi t is very large, 1 over xi t is very, very small. So that means that when I'm drawing that tau t from this distribution, I might have things going to 0. Okay, the inter-event time goes to 0. And I'm going to illustrate this by actually showing you how to implement Gillespie for real without using a package. So I'm going to do a very simple birth and death process. So individuals are born at a per capita rate B, they die at a per capita rate D, and I'm going to, so if B equals D, the population can remain essentially constant, but if B is larger than D, you expect the population to explode, and if B is smaller than D, the population will collapse. And let's do a classic Gillespie for this. So go back to what I was saying. So Gillespie for this looks like so. So I set my initial time t0, my initial population n of t0. I compute the weight of the events, which in that case is simply B plus D. I draw tau t from an exponential distribution that has parameter xi t. And then I determine which of the two events, birth or death, which of the two events, birth or death, took place. And if I have a birth, then n becomes n plus 1. And if I have a death, n decreases by 1. So let's implement this. Let's start with b equals d equals 0.01. So if I do that, if you think about the model, like the equivalent ODE would be n prime is b minus d n. So if b equals d, then n prime equals 0, so the ODE would not change. So the stochastic system, it's going to be a bit different, but you see what the underlying idea is. I take an initial population of 100, and so I need to store the state, so I just have t and n that are going to be the variables in which I store the state, and I want to compute over 1,000 days, say. And of course, I need to know where I am, so I'll track also the current state and the current time and current state. And that's Gillespie. So that's exactly what I was explaining. Oh, that's okay. I don't need to move myself. That's what I was explaining with the former algorithm, the previous algorithm. So while the current time is less than my final time, I'm going to compute xi t to be the sum of b plus d times the current number of people in the population. Just to be on the safe side, because sometimes you'll get n equals 0, and the exponential random number generator doesn't like if you give a parameter of 0. So what you do is, if you have n, the current n is equal to 0, you just break, which means that this is going to take you out of this loop, okay? Because at that point, when n equals 0, I'm done. I can't have ex nihilo birth, so I have n equals 0, and n will remain 0 for all subsequent times, and so I can just stop. But if I don't have 0 individuals, if I have a positive number of individuals, I then compute tau t, the time to the next event, by using a randomly an exponentially distributed random number, a single random number with rate xi t. Okay, so this xi t that I've computed. I say that my current time is shifting by this tau t that I've just computed. I compute my vector of probabilities, and you can see that I'm putting the weight of the first event. Sorry, the first, yes, it's B here, both. And the other one would be B n-cur plus D n-cur, which ends up being psi t. Okay. And then I take a uniformly distributed random number, a single one, between 0 and 1, and I find which entry in V matches that which interval in V contains that value of zeta t, and I need to shift by 1 because of the way find interval returns values. And depending on this position, I either have both, where I increment the number of individuals, or def, where I decrease them. And now I add this current state to the vector of n's and the vector of t's that I already have. This way I store the result. So when I do so, yes, this is just a remark in passing. So if you're using R, it's there's a very good bunch of functions to generate exponential distributions. This is just a trick. If you're using code in a program that doesn't have a good exponential distribution generator, this is just to show you that once you have something that's exponentially distributed, you can generate that number by simply taking a random number in 0, 1, and then making this transformation. And that transformation will give you an exponentially distributed random number. Okay, so this is just a remark in passing for those who would try to implement Gillespie in a context that is not R. So what do we get? So this is one solution. So here I'm indicating both and def are equal, and I've taken a solution. So I start at n equals 100, and you can see that as time goes, I first go down, then I go up, then I go down, etc. This is a case where def is higher than both. So in that case, we know that the solution is going to collapse, and yes, it does. You can see that we start at 100, we go to 0, and remember that I said if you hit 0, you stop, and here I've hit 0 around 350, or a little before a time 350, and therefore the simulation has stopped. But now let me show you the bad case. So remember, I start with 100, but what's happening as time goes, my population explodes. Okay, so I've put birth 2.5 times a death. The population explodes, and you can see that time here, I was hoping to go to 1,000, but at this point here, I stopped. Okay, why did I stop? Well, let me show you here. I wanted 1,000 time units, and I stopped at 473 because I was losing patience. So at the stop time, I got a total population of 241,000, and time was moving very slowly. So this is the tail, so the last few entries in diff of t. So t is my time. Diff of t is the difference between two time points. And so you can see that I'm at 1.3 e to the minus 4, 1.2 e to the minus 4, 5 e to the minus 5, etc. So the increments in time are to the order of 10 to the minus 4, 10 to the minus 5. And I'm trying to do 1,000 days, but I'm progressing forward where each day is going to take me about 1,000 iterations, and it gets worse and worse. And let me show you, this is the inter-event time in that simulation I was showing you as a function of the time. So when you start, the inter-event time is somewhere between 0, sometimes not a lot happens, but 1 or even more. And then what you can see is that progressively, as we progress, the inter-event time becomes smaller and smaller and smaller. And it eventually goes to values which block us. Okay. And that's where an algorithm called tau leaping can come and help. So I'm not going to show you, to explain how tau leaping works, but I will show you how to use it in the practicum. The idea is essentially that you consider groups of events rather than a single event at a time. You suppose that there's groups, but it is an approximation method. So the Gillespie method gives you exactly what the Markov chain should be, whereas the tau leaping, which was also worked on by Gillespie, I have to point out, this gives you an approximation to the solution. Okay, but there's two good packages, Gillespie SSA2 and Adaptive Tau in R, that allow you to do this. There's probably others, but that's it. Okay, and that's it for this lecture.